Welcome to this section on worked out problems in projection of solids. The first problem we'll be looking at is rather simple. So we have a hexagonal pyramid which is resting on its base, that is that it has a base edge 45 mm and altitude 85 mm, resting on one of its base edge on the horizontal plane with its axis inclined at 35 degrees to the HP and parallel to VP. Draw its plan and elevation. So basically we need to draw the top and front views of this final position. So as usual, we'll start with an initial position which is suitable for the next stage of positioning it. So we'll see how this is in 3D first, and then we'll go to the construction. So what you see on screen is a hexagonal pyramid resting on its base. So if we look the pyramid from the top, you could see the edges positioned this way, the base edges. So that why we have specifically positioned in this ways, the reason is while constructing we will be using this particular base edge with respect to which we are going to tilt this solid. So for example, if we try to tilt this in 3D, say we can tilt this with respect to this base edge. So that would be the tilting. So the question says that it is being tilted with respect to the base edge and the axis is inclined to the horizontal plane at an angle of 35 degrees. So one thing you can keep in mind is that if the axis of this pyramid is at a particular angle, the base will be the complement of that. That for example, if the axis is at say 30 degrees with respect to the base, correspondingly the base would be at 60 degrees to the base. The reason being the base and the axis are perpendicular. So this is one point you will have to keep in mind while constructing the solid. So the final front view will look like this, and you can see some hidden edges inside. You could see these faces, slant faces are visible, and if you look from the top, and this would be the view, and you could see that these, the inner edges, that is a base edge with respect to which it is still getting tilted, so that would be hidden definitely. And based on our thumb rule, all the boundary edges will be always visible, and we look at the visible faces when we look from the top. You can see that since we are looking from the top like this, so this edge, this face and this face as well as this face is visible, whereas this bottom edge and these faces, these 1, 2, 3, these faces are actually hidden. So that's exactly what we get when we look from the top. We have the 3 slant faces and these edges getting hidden and these upper ones getting seen. So let's see how we can construct this. Draw the hexagon such that the edge, one of its edges in this direction, that is one of the base edges is perpendicular to the XY line, so that you have the provision of tilting this with respect to this edge in the front view in the next stage. So all these corners, all these slant edges are marked. All the corners and the center, everything is projected up. The suitable required base and height dimensions. The next stage, we are actually tilting. With respect to the axis. The axis is 35 degrees. It could be either like the axis is 35 or the base as 55. Both are right, because combined together they should be 90. So once you position that, so this particular edge actually will be representing A dash and B dash, actually, even though only A dash is shown for clarity. So we actually have two edges there, two vertices there. So we project from all corners and edges. And once you project from all both the top view of the first stage and the front view of the second stage, the corresponding positions, for example, this point is B, and B will be coming here, since this is A dash B dash, this is A dash B dash. So this is point B, and this would be point A. So like that, you locate all the corners, and this would be the apex point. So project from here and here to get the apex point. Now join from all the corners to the apex first of all, and once you complete that, then based on the visibility rules, you will decide which will be seen and which will be hidden. So you could see that the boundary obviously should be continuous and visible, and those edges which are passing through faces. So this is a particular face, and these edges are passing or cutting through faces, and they have to be hidden. So let's pass on to problem number 2. So here the question is to draw projections of a hexagonal prism of side 20 mm and axis 16 mm, and again it's resting on one of its base edges as the previous case, and the axis is inclined at 40 degrees to the ground and parallel to the VP. So let's see how we can solve this. So we'll draw the prism in simple position. That is, we draw as if the prism is resting on its base, and we will suitably position the edge so that we can tilt with respect to that. So the edge AB is made perpendicular to XY line so that we can tilt with respect to that edge in the next stage. So we draw projectors from all the corners, and we draw the front view now. And we mark the positions. So please note that this is actually A dash B dash. We are not showing specifically to make sure it is not cluttered, and this is for clarity that we are not showing this point as A dash B dash, but this has to be A dash B dash. and we tilt the solid now. With respect to the required angle. So that is 40 degrees with respect to the XY line, or with respect to the horizontal plane. Again, draw projectors from all the position, all the corners or all the vertices, from the front view as well as from the previous top view. And where the corresponding points meet, we have the projection points. So for example, this A dash, B dash, and this AB. So like that you mark all the corners. So in the case of prism, there will be more number of corners than a pyramid. So here these edges are going to be hidden. And you could see that the inner edges, they become hidden, and the inner vertical two edges, they also are hidden. The boundary becomes visible, and these faces, the top 1, 2, 3 faces are visible, and the bottom 3 faces are hidden. Now let's look at another problem. So the question is, draw the projections of a cube of 60 mm edge resting on one of its corners on HP when the body diagonal of the cube is perpendicular to VP. So this question requires some explanation with respect to what is the importance of this particular problem. So and also how this is oriented in space. So let's look at the orientation of this cube in multiple positions in a 3D software, so that it will be much more clear to you. So what you see on screen is a cube which is positioned on the horizontal plane, resting on one of its faces. But the question says that the cube has its body diagonal perpendicular to the vertical plane. So you can see that the cube is simply resting on one of its faces. And let's first of all see what is actually meant by a body diagonal. A body diagonal for a cube is nothing but the line joining the opposite corners of the cube, any of the opposite corners. For example, this corner to this corner is a body diagonal. Similarly, this corner to this corner is a body diagonal. So for that matter, any one corner to the opposite corner across the solid cube is the body diagonal. And the question says that it is resting on a corner. That is one thing. Second is, the body diagonal is perpendicular to the vertical plane. So this has to be thought of in two steps. First, let us rotate the cube in such a way that we'll have the corner suitably positioned so that we can tilt it with respect to that corner. So what we'll be doing now is rotate the cube. So let's try rotating the cube 45 degrees with respect to VP first. So now we could see that if you look from the top, now the cube has been rotated 45 degrees, so that when we look here, we get a corner here. Instead of a face, instead of a base edge, now there is a corner, so that in the next step, when we try to tilt it, we have a corner suitably positioned. So with respect to this, you can easily tilt this solid in the next. When we actually draw the position on a sheet of paper, we can actually take this particular point and rotate the cube in the front view. So this will help in doing that. Now the next step would be to rotate, so that rotate and see basically how we can make the body diagonal perpendicular to the vertical plane. So before making the body diagonal perpendicular, first of all, we need to know that this body diagonal, let us take this body diagonal, the line joining this point and this point. So this is now currently at an inclined condition. So the steps would be to, first of all, rotate this body diagonal so that that is parallel to the XY line, or for example, or parallel to the horizontal plane first. And then if you tilt it, rotate it 90 degrees, now it will become perpendicular to the vertical plane. So let's see how this is practically possible. So we'll try to first of all rotate it. So now it is rotated. If you look at the front view, you could see that now the body diagonal, that is this point to this point, it has become parallel to the XY line. That is, this is nothing but the body diagonal. This point to this point is a body diagonal. This corner to this corner. So that has become parallel to XY line and parallel to HP, but it is still not perpendicular to VP. So what we need to simply do is, since it is parallel to the XY line, if you need to make it perpendicular to VP, you simply rotate the cube at this point by 90 degrees so that this body diagonal becomes perpendicular. So to make it more clear, say let's draw the body diagonal like this. For example, we have the body diagonal be somewhat like this. This is a body diagonal. Now it is actually parallel to the XY line, and it is also parallel to the VP now. Now we need to make it perpendicular to the VP. To do that, we have to rotate the cube by 45 degrees. So what we do is, let us try to rotate it now. Has become perpendicular to the vertical plane. So it is clear now. So now if we look from the top, now this is the body diagonal that has become the line joining this corner and this corner, that has become perpendicular to the vertical plane. So the interesting thing about this position is that if you look from the front view, what you actually see is a isometric view of this cube. When we learn about isometric, it will be clear to you that when a cube is positioned in this manner and projected in the front view, what you ultimately get is an isometric view. And to see it more clearly, let us make it into a solid view with the hidden edge visible, so that now it is much more clear to you. And so this is a typical isometric view where you could see all the three faces. So this is again a projection. So this is the importance of making body diagonal perpendicular. There is a body diagonal between this point and this corner, this corner and this corner. That is perpendicular to VP. So there is a golden angle which makes this possible actually. So if you take a cube, rotate it at 45 degrees to VP, and then rotates one of its bases at an angle of 36.25 degrees with the horizontal plane, you get this position. So this particular peculiar angle of 36.25 is required so that the body diagonal becomes perpendicular, or body diagonal become perpendicular to the vertical plane, or they lie in a horizontal line. So to make that we need this particular angle. So these things you will be learning in isometric projection. So basically, looking at the steps, we first of all, what we did is we rotated the cube so that by 45 degrees, so that in the top view you get the corner. So the next step, we rotated with respect to the horizontal plane, so that the body diagonal becomes parallel to the horizontal plane and parallel to the xy line. And then again we rotated the cube 90 degrees with respect to the vertical plane, so that the body diagonal became perpendicular to the vertical plane. So this is the three-step process by which we have achieved this. So let us now see this in practice, how to actually construct this projection. So we'll start drawing the xy line and then the solid in a particular position, that is a cube in this particular position which we have seen before, that is so that the corner is on one side, and then from there we project the corners onto the top view to get the top view. So if we join the points, corresponding points, the height, since it's a cube, this particular height will also be 60. So we can see this particular edge here. So that would be the front view, the first position. So in the next position, what we'll be doing is we'll be tilting this solid with respect to this corner, so that, and before that we join these body diagonals E and C. E and C is a body diagonal that has been joined, so that enables us to actually rotate this solid and make this diagonal parallel to the xy line, as we have seen before. So that view is also there. Now the next thing is simply project it down and project from this view, so that you get the current top view. You draw projectors from all the points. Basically, this line is drawn so that the body diagonal and this perpendicular is drawn, so that it will be easier for you to construct this solid. That's the reason why you have joined this perpendicular. So basically you draw this line horizontal and this line here, and from which you can construct the remaining portions. That's the reason why we specified it. And then we are actually completing the top view as well. So once you complete the top view, the next step would be to rotate this top view so that this body diagonal which we have drawn in this top view, so when we rotate this top view by 90 degrees, what happens is this body diagonal becomes perpendicular to the vertical plane. That's exactly what we are going to do in the next step. So you can see that the hidden lines are also drawn here. And so now the next step would be to draw projectors from all the corners as usual, and then draw the final view. You also draw projectors from the second front view, and where the corresponding points meet, that will be your final front view. So as we have seen before, this is nothing but a typical isometric projection. So you could see that the other edges which is behind, the edges behind are actually hidden from view. So that completes this problem. Thank you.